Right, hello everybody. Let's crack on. So, hi there, I'm Adrian Jeakins. I'm Director of Engineering at Brompton Technology, and I'm here to talk to you about TrueLight, our new feature we're launching at NAB2023. So, before we talk about what TrueLight really is, we need to talk about the state of displays at the moment. Next slide, please. Superb. Cool. So, at the moment, displays like the one we've got here, they use red, green, and blue to create the light for each pixel. Why do they do this? Well, it's because we as humans see in RGB. So if we look at the spectrum of a standard LED display, we can see that there's no light in the yellow-orange region at all. And yet we can produce colors in that region to the eye because the eye sees in RGB. So this is a completely standard, normal thing. This works great for direct view applications such as this display. And because RGB works so well, that's how all our video systems work. They're end-to-end RGB. And that means that given an input signal, there's effectively one correct solution for the color of a pixel. If we know our output transform and our color space, we know exactly what color that pixel is meant to be. And that's important. I'll come back to that later. Next slide, please. So displays like this have been around for a long time, but recently they found a new application in virtual production. And in virtual production, the display has two purposes. It's both the background that we see the actors and the objects on, but it's also a light source. It illuminates those objects and those actors. And that's where we run into one of the problems with RGB. Next slide, please. So by their very nature, in order to produce saturated colors, RGB displays have very narrow, spiky spectral output. And that means their color rendering, their ability to illuminate things, is actually very poor. And we can trade off some of that saturation, that ability to reproduce those colors and get better color rendering by making our emitters more broad spectrally. But that then means that we can't achieve those saturated colors that we want to with our displays. Our color gamut is effectively reduced. So what's the solution to this problem, this trade-off? Well, we're proud to present TrueLight, which is Brompton's solution to this problem. Next slide, please. So TrueLight is a no-compromises solution to this problem. There are some products on the market that can offer part of our solution, but they can't go as far as we can in terms of the compromises they make. So TrueLight enables 4-color LED panels with no compromises, fully per pixel luma and chroma calibrated, with all the standard feature set of a Brompton display that's essential now for virtual production. So before we talk about the science and the technology, let's have a look at what this actually looks like, some images. We can go to the next slide. So this is a standard color checker chart under RGBW and RGB illumination, with RGB in the center and RGBW on the outside. And what we can immediately see if we look at our primaries is that red is very, very oversaturated under RGB illumination. Our grayscales are generally preserved. There is a little bit of a linearity shift in some areas, but generally they look fairly consistent. But our reds, our cyans, and our oranges are shifted quite spectacularly under RGB illumination. In the top right-hand corner, we can see the skin tone chips, and we can also see how those are shifted towards magenta. So what does this look like when applied to skin tones? If we go to the next slide, you'll see what this looks like. So on the left-hand side, we've got illumination under RGBW, and on the right, we've got RGB. We can see the massive, massive skin tone shift. Our model almost looks sunburnt under RGB illumination. And if we go on to the next slide, we'll see an example of what this looks like composited against a background. So we can see that under RGB illumination, those red shifts mean that our model doesn't blend into our background at all. And when we solve that with RGBW illumination, we get a much better blend. And given the entire point of virtual production is to put our actors and our objects into a virtual environment, to light them with that environment and have it look realistic, this is clearly a major problem. So what's going on here technically? If we jump to the next slide, we'll have a bit of a look at some spectra. So this is the real spectral output of the panel that we've been seeing illuminating objects in those previous 3 slides. So in direct view, you can see we've got very spiky spectral output. There are big gaps in the spectrum, particularly in the cyan areas and even worse in yellow and orange. When we add our fourth emitter in, and this, bear in mind, this is producing the exact same white point output around 6500 Kelvin D65, we can see that our spectrum is massively smoothed out. We've got really nice illumination in that yellow and orange region. So that improves our color rendering a lot, and that's what we're seeing in those previous two slides. For a Brompton solution to be of the standard that we want it to be, it has to be fully calibrated. So that's what I'm going to talk about next. Can we go to the next slide? So our calibration system at Brompton is completely unique. We built our own from scratch because there was nothing on the market that would offer the performance that we wanted. And while it was initially designed to handle RGB panels, all the hardware is there to handle any calibration of any panel, including these new ones that have a fourth emitter. So our Brompton system, we offer a completely different approach to calibration, which we call dynamic calibration, which means that our color targets are not fixed in the factory like a traditional calibration. We offer the user completely flexible color system at runtime. And that extends to our TrueLight implementation. Using the Hydra system, we're able to offer full per pixel correction of luminance and color. At Brompton, we've been talking about RGBW. But for us, the W doesn't stand for white. It stands for whatever. We're able to cope with any fourth emitter, both in and out of the gamut. So that could be a warm white, as in the panel we've seen today, or it could be a gamut extending cyan, a cool white, an amber, or basically anything you like, depending on what you're trying to achieve. The calibration system deals with this entirely. There are no firmware updates to deal with different emitters. It's completely a calibration problem. Alongside dynamic calibration, we've developed several state-of-the-art features that improve color performance. Pure tone, which linearizes the output, giving us accurate EOTF tracking, and thermocal, which compensates for thermal effects within LED panels. And both of these carry through into TrueLight. If we go to the next slide, I'm going to talk about some of the problems that you run into trying to build a real practical system that uses these fourth emitters. So the first one is metamerism. If you recall at the start, I said when we have an RGB video signal and an RGB display, there's effectively one correct solution. But if you consider trying to produce white using our RGBW display, there's two ways we can do it. We can use the RGB LEDs, or we can use the white. So which should we choose in a particular situation? How are we going to solve that problem? We've got an infinite set of solutions. Which one does our user want? Because we have two ways to produce white, we could do them both at the same time. That's going to give us brighter output, great for specular highlights, the sun in our displays. But it comes at some costs. So is that appropriate? Should we do it, and when? Our colorimetry is then designed to deal with the human eye. But cameras don't see the world in the same way as the human eye. They have a different spectral response. So our colorimetry is then inaccurate. So we need to solve that problem. And finally, the complexity of this maths to convert from RGB to RGBW is quite considerable, especially if you want to do it in a fully calibrated way. So these are the problems. On the next slide, I'll tell you about the solutions. So to solve the metamerism problem, we have a feature called spectral preference. Spectral preference allows you to tell the system how much of the fourth emitter you'd like to use, from 0% using none to 100%, where the system will use the fourth emitter as much as possible while retaining color accuracy. For our brightness problem, we have spectral headroom, where you can allow the system to use all four of the emitters together to produce bright specular highlights, for example. This will be done intelligently, so it's only when it's needed, in those very bright areas of the image. In areas that don't demand those high brightnesses, we retain the complete spectral output smoothness as specified by spectral preference. We then have spectral balance, and this allows us to tune our our white performance by adding or subtracting small amounts of RG and B to tell the system what the camera sees white as. To go alongside this, if we have a look at the next slide, we've got a dynamic user interface that really helps you to understand what's going on. So here, on the left, we've got spectral preference at 0. In the middle, we've got it at 50%. And on the right, at 100%. What we can see is we've started off with this very spiky spectra that we saw earlier. And on the right-hand side, we've got our very smooth spectrum. And in the middle, we've got something in between. So this is really helpful for understanding what the system is actually doing and the performance that we're getting. So I've talked about the processing system, but we also need panels to go with this. And we're very proud to be showing at NAB 2023 the first panel that supports the Brompton TrueLight system. Next slide, please. So that panel is the Row CB5 Mark II RGBW. So this is built on the Row CB Carbon Series platform, uses the same rigging, but each pixel has RGB and a warm white emitter. So this actually gives us very good color rendering across a wide range of color temperatures. And this panel is in fact what you've seen in all the images that I've shown you. If we look at the next slide, I'm an engineer, I love a bit of data, so I couldn't let go without showing you it. So on the left, we can see the actual spectra that this panel produces at D65, on the top in RGB, on the bottom in RGBW. So we can see that beautiful spectral fill-in that we've been talking about that gives us that better color rendering. In the middle, we can see the comparison of the CRIs this panel produces in these two modes. CRI is a little bit of a dated measurement, but it's very visually impressive how much the improvement happens. You can see, for instance, that our red score under this condition is actually negative. It's really, really bad, so bad that the chart doesn't even show it under RGB illumination. That's how inaccurate our red color rendering is. And you can see it's massively improved in the chart on the bottom under RGBW illumination. Finally, on the right-hand side, we can see some TM30 measurements, a rather more modern color rendering metric. And for those who are familiar with TM30, our fidelity score goes from around 60 out of 100 to 82 out of 100, a very meaningful improvement. TM30 also gives us a very nice visual way to look at color rendering. So you can see there are two circles, what are meant to be two circles anyway, a black reference one and a red one showing what our color rendering is actually doing. So in the RGB case, you can see what's meant to be a lovely circle is very distorted, particularly in the oranges, the reds, and the cyans, where we don't have any light in our spectra. And when we introduce our white LED, we can see that circle becomes a lot more circular as it's meant to be. So finally, on my last slide, some applications for this. Now, we've obviously talked about virtual production and extended reality, where we're illuminating people and objects with these screens, as well as providing the background. And that's a very obvious application. But really, this extends to anywhere where an LED screen is illuminating an object. So think about fashion, retail. In those environments, there are colors that our designers have very carefully picked. And when those are illuminated under RGB illumination, those colors are going to look wrong. The balances are going to be completely off. And further, consider the metaverse extended reality boardroom of the future, where one whole wall is an LED screen which you see through to your colleagues across the world. That's all very well and good. But if the light quality that it comes off it, illuminating the people in the room, shifts them horribly into red, as I like to say, making them look like lobsters, that's not going to be a very pleasurable experience. It's not going to be a nice place to be. So we think there are a lot of applications for this improved color rendering beyond the traditional VP-XR, which obviously will need it. To round up, next slide, thank you. This is TrueLight. It's best seen in person, so please come down to our booth if you're at NAB 2023, or visit one of our offices around the world and see it for yourself. Thanks very much.
Thank you. And if you're not working in this field, you don't understand how important some of this stuff is. But those of us who are trying to push the boundaries really appreciate this kind of work. So let's see, does anybody have any questions out there?
Sorry. You've mentioned that you're working with Row LED with TrueLight. Are you planning on expanding with other LED manufacturers in the future?
Very good question. So, like every feature that Brompton produces, we are completely agnostic. Because we're using the new G1 receiver card to drive these panels, it's a very new thing. So we kind of picked up one panel manufacturer to work with to start with, just because we needed to iron out all the bugs, and it's simpler to do it with one. But this process will be available to every panel manufacturer. And it's also worth saying that we're starting with very coarse panels that are bright and generally used for virtual production ceilings. But we expect that technology to expand out and be available on all kinds of LED panels, right down to the kind of pictures that we're seeing here today.
What about those who already have an LED with Brompton processors? Are they able to upgrade or change their processors?
Another good question. So the G1 receiver card is compatible with our existing SX40 processors. And so there will be an upgrade path where you can just update your panels, but you don't have to update your processing. So that will be the upgrade path. It will be compatible with our existing and future processors.
All right, excellent. Any other questions? Nope. Well, thank you so much, Adrian. We really appreciate it. This stuff is absolutely wonderful. We're really excited about it. Thank you.
Great stuff. Thanks for having me.